Hello, this is Jim Corkins, and we are continuing with the module on light, and we are now into curved mirrors, which is 7.4. If you haven't done so, please do the readings. Chapter 23 and 24, specifically 24, is about curved mirrors and lenses and geometric optical objects. Also, please do the sapling homework. Well, please do your homework. All right, please start on that. Here we go. So with spherical mirrors, we're going to be doing ray tracing, and we're going to be doing more than one light ray. So from the last chapters, we were only kind of tracing one light ray as it passed through different substances or different mediums or reflected off of surfaces. Well, now we're going to have to, with lenses and also with spherical mirrors, we are going to have to do multiple light rays, okay? And there are two types of spherical mirrors that we're going to be working with. One of them is a concave mirror, and what that does is that focuses lights so the light rays converge on a point, okay? So it's also called a converging mirror, but most of the time most people refer to it as a concave mirror. And just think of a cave, right? So it's bended. Well, the center of the mirror is further away and the edges are out here, so you can see that, right? There's another type of mirror that is called a convex mirror, okay? And what a convex mirror does is the light rays actually diverge away from a focal point. So if the focal point is right here, they're diverging away from that point. And what happens is through ray tracing, and we'll talk about this, is that they will, it's almost like, actually it looks like they're diverging away from this point right here. So this is the point at which they're diverging. So this would be the focal point. And if you think about it, this is also called this is called a diverging mirror. And so what is kind of going on is if you look at it, and I'm going to mark this document up, the focal points actually exist on a mirror. Excuse me. Where, so if this is the concave mirror that I said was kind of like a cave, if you look at it, and this is a rounded shape, if it continues to round, right, and I'm going to try to continue to round this, it starts to look like that maybe the radius of that, what's starting to look like a circle, is way out here. And what we find out, this is the center. This is called the radius right here. So this is the radius of this circle. And the focal point, what we'll find out, which is this weird cursive F, will exist at a half radius, okay? With a diverging mirror or a convex mirror, it also has that same circular shape, right? Oops. Let me draw that. However, the focal point exists on the other side. And this is the point with a convex mirror, if the rays are coming from the other side of the mirror, that they're actually diverging away from this point. And so the radius appears to be about right over here. And the same thing, what you find out is the focal point, or here the diverging point, which is also known as a focal point, it also occurs at the half radius of this sphere. Okay? But in the beginning, we are going to just study concave mirrors. So we're going to move on, and we're just going to work on concave mirrors, and towards the end of this lecture, we're going to work on convex mirrors. So now, before we actually move on to talking about those different types of mirrors, let's talk about there's this thing called a mirror's equation. It's a mirror equation, okay? And So here's what we have. We're assuming the light rays are always coming from the left side of the page to the right side of the page in these drawings. Okay, so I'm going to draw the light rays coming in. Okay, so if you have a mirror, this type of mirror, if you could remember, what type of mirror is this? If the light rays are coming from this side, what do you think the mirror would be doing? Do you think it would be sending the light rays towards this focal point or away from it? So this would be a concave mirror, so it will be focusing the light towards this focal point, right? So this C is the center of curvature. It's also the radius of, it's the radius of this circle, right? The center of curvature, which is C, is also the radius. And I'll write those here. Okay, so that center of curvature is the radius of, if this were to complete a circle, or this diverging mirror would complete a circle. So this is a concave mirror, and this is convex. Okay, and so here's the focal point of the concave mirror. The mirror is right here. It's a reflecting surface. This line right here is called the principal axis. Okay, and this principal axis bisects the mirror in half. It cuts it in half. Okay, so what I wanted to show is that if you have an object over here, and typically when we draw objects, we're going to be drawing them as arrows. And here I'm going to draw an object. Here's the object. So the distance from the object to the mirror is going to be subscripted distance sub O. So that's the distance of the object to the mirror. Now, with this type of mirror, an image will form on the opposite side, and let's ignore this for a little bit, and what we'd find out is that an image would form over here, and we'd put an I for that, and so the distance from the image to the mirror, where the image would form, is the image distance. Okay? Well, what we found out is that the object distance, 1 over the object distance plus 1 over the image distance, is equal to 1 over the focal point, right? And there's a proof for that, and that is in the supplementary material from Khan Academy. Okay, so if you wanted to see that, how this equation came about, you could watch that, right? And what we had learned before, that the focal point occurs at a half the radius of this object, right? Of half radius of the mirror. If you continue this mirror as if it were a complete circle. So again, a concave mirror is concave towards an object. A convex mirror, if this is where the object is now, the convex mirror is concave away from the object. Okay, or it's also called convex towards the object, which is an interesting way of saying that. So we're going to investigate in the beginning concave mirrors, right? And we'll do that now. I had forgotten to say that there is a magnification thing too. If an object, how you calculate the magnification, and what the magnification is it's the size of the image compared to the size of the object, right? If the image was super big, like this big, well then this would be a magnified image. So this would be a magnified image if the image was really large in comparison. So this is the image. If this image, this size of this thing is really large in comparison to the object. So when I talk about magnification, I'm talking not only about the size of the image compared to the size of the object, also known as height, but also it's the image distance over the image object distance can be used to calculate magnification. So back here, if you compare this distance here to this distance, and this can't happen at a shorter distance than the object, right? So if an image this big, realistically would be way out here. It'd be the distance that the image is to the concave mirror would be related to how big the image is. Okay, so the image distance would be way over here. It's my neighbor who is a motorcycle rider in the background. Sorry about that. Anyways, so this image distance to an image this size is proportional to the size of the image over the size of the object, right? So that's another way to calculate magnification. So besides this equation being used to calculate distances of objects and images related to the focal point, you should also calculate the magnification of the image in comparison to the object height or distance. Okay. Incidentally, if this works out, if a negative m value, if this works out to be a negative value, and I notice in the equation there's a negative already there, but once you calculate this, if this works out to be a negative value, and I should actually put this here as a magnitude, this is more of a magnitude of the image without a negative there. I'm just looking at this right here. If this magnification right here works out to be negative, that means the image is going to be inverted. So this image is inverted, and so this would work out to be a negative number, even with this negative here. Okay? And we'll talk about this when we go through this. All right? So there's some steps into drawing light rays for a concave mirror. Okay? So what you're supposed to do is you're supposed to draw the optical axis, which would be this horizontal axis. The first step is drawing the actual mirror and drawing the optical axis. So this is the optical axis. And then you're also supposed to draw the reflective surface, right? So if I was going to draw a concave mirror, I'd draw the mirror first. I'd draw the optical axis that would bisect the mirror in half. Okay? And then what you're supposed to do, you're supposed to represent the object with an upright arrow at a distance S or D sub O. Okay? So go ahead and draw where the object is, right here, and I always label it with an O. And then I guess what they're saying is this: you should always draw the distance that is. So you could call this d sub o, and it's understanding that this distance from here to the center of the mirror is that distance do, or just s. Okay? And then he says what you're supposed to do is to draw 3 special rays from the tip of the arrow using a straight edge ruler so that the rays reflect off the mirror plane. So the first one you are supposed to draw is a parallel ray to the optical axis. This is also called a parallax ray. Okay, so this is the parallax ray. So when you draw this, you're supposed to draw it from the tip, and I'll use a different color for the parallax ray. The parallax ray, which I'm going to be using, is red. It goes from the tip to the optical axis. It's parallel to the optical axis. The optical axis, again, is right down here. I've labeled it here. To the reflective surface, right? So it goes from left to right. Okay, and you don't have to actually put arrows on it if you don't want to. It kind of helps, though. And then what's going to happen is it's going to go down through the focal point. Now, I never indicated the focal point on this. So the focal point, I'm going to just arbitrarily set it to be right here. Okay, and I indicated that with an F. And that would be, this is not only labeling that this is a focal point, but it's also implying that the distance from here to the reflective center of the reflective surface is the distance F. Okay? So this red light ray, which goes here, I'm supposed to be using a straight edge, is going to hit the surface of this mirror, and then it's going to bounce through and down through the focal point. Okay? And so I put little arrowheads on the end of that. Okay? So we just drew the parallel ray, or it's also called parallax ray. All right. Now what you're supposed to do, it says you're supposed to send in another incoming ray that passes through the focal point and emerges parallel to the plane of axis. Right? So now we're going to draw another one, and this is going to be called a focal point that will be a ray passing through that focal point. So this is another ray. I don't think it really has a name. It's just, I'm going to call it maybe the focal point ray, and I'm going to use blue for that. And this one's going to go from the tip of the object down through the focal point. Okay, so it's going down through that focal point, and when it hits right here, it's actually going to be parallel to the optical axis. Okay, so that's another one. Okay, and it probably is hitting right over here. Okay, so it looks like they're kind of starting to intersect right about here. I have to do a better job at, I should have probably brought out a straight edge, so I apologize. Finally, you're going to be drawing a last ray directed at the center of the mirror. Okay, so this next ray, what I'm going to draw is, I'm going to use green. Should I use green? Yeah, I'll use green. So this next one is going to go down through the center of the mirror. So it's going to hit the center of the mirror. And then it's going to reflect off that center of the mirror at the same angle that it hit. And it looks like it's also intersecting that red that red parallax ray. And I'm going to continue this one on so you can see how they're all continuing in this direction, right? So it looks like they're all merging right about here, and this is where the image is going to be formed, and I'll use pink for the image. So this image is going to be straight down, and this is the image, right? This is where you would label this D sub I or S prime, depending on which textbook you're using. Okay? And so now you've labeled all three of these special rays. And it says make sure you extend the rays as much as you can so that they converge at some point, which is what we did. And then make sure you label your distance, your image distance, as S prime or D sub I. And that will, this distance from here to the center of the curved mirror, or the concave mirror, is going to be the distance, that image distance, right? And that's what we would be using to calculate in here, as well as the magnification here. Okay? And that's basically the basics of drawing concave mirror lines. And you're going to be using a parallax ray, a focal point ray, and then a center of the mirror ray to do that. And make sure you can see how terrible mine turned out if I didn't use a straight edge. So it's best to really use a straight edge. Okay. So when we're doing concave mirrors, there really is only only two types of drawings which we really need to do. And you don't really need to draw all three rays. But I'll show you all three rays when I draw them here. Let's just make sure that I can mark up the document and close it. And now I have my tools, and I'll turn this to black. So here we go. So with a concave mirror, as we just saw, our object was in between, in the last slide, our object was in between the radius of this circle and the focal point. So when we drew this, we drew a parallel ray or a parallax ray, and it went straight across, hit the mirror, and went down through the focal point. We then drew another focal point ray, which went immediately from the top of the object to the focal point, and then straight across. And then we drew a center of curvature ray. And you know what? I think it might be better if I just use some of those shape tools. So I'm going to draw a line here. And then I'm going to draw another line with another shape. And we're going to draw another line. Okay, hold on a second. Kind of getting used to drawing these. Draw another line down through the here. And so you see here, and I'm going to call this the reflected or center of mirror line, where you've got two rays. You draw a ray, and it's actually probably better if I just draw it like that. Anyways, so as you can see, all three of those rays, the parallax ray, the focal point ray, and the center of mirror ray, all come down right here, and our image is going to be inverted, so it's inverted. It also looks like it's bigger than the object itself, and this is also called real. if you notice, the rays that we're using are solid lines, right? And that the image is forming on the same side as the object. Well, with mirrors, that is called a real image. A real image is when the image forms on the same side of the mirror as the object. It's going to be different when we talk about lenses, but for mirrors, a real image is on the same side of the mirror as the object. Okay. Notice that if our object is moved outside that radius, then our lines that we're going to draw, I'm going to try to free draw this, hopefully. Our parallax ray is coming straight across down through the focal point. Then we have a focal point ray coming straight across, hitting the mirror, and then reflecting parallel to the optical axis. And then, I bet, if we draw this, it's also going to intersect, and it looks like it does. So that's the center of mirror ray. And again, yeah, there you go. So notice that they're all three converging right here at this point. Okay, and notice that the image, that image is going to be upside down, so it's called inverted, and it looks like it's smaller. It's demagnified from the object. It's smaller than the object. And it's on the same side as the mirror, so it is called real. Okay. What happens when the object is in between the focal point and the mirror? Well, again, you're going to draw a line straight across, a parallax ray. It's going to bounce off the mirror and go down through the focal point. But here's the weird part. It's not really going to converge on any one of the lines that are coming through on the same side of the mirror. So the parallax ray is coming through. Then we draw a down through the focal point ray, which is weird because we can't draw it. If we draw down through the focal point ray, it's just going to go off. It's not going to bounce off. So what you have to do is draw from the tip straight up here, and it's going to make a dotted line. It's almost like an implied line, and then comes across. And then the down through the center of mirror ray, a center of mirror ray is bouncing off the center of the mirror and coming in at the same angles there. And notice that their implied lines, the dotted lines, are forming on the opposite side. So the image in this case is going to form on the other side of the mirror, and that's why it's called virtual. It's also going to be enlarged, and it's going to be upright. So whenever you have an object in between a focal point and the actual mirror, you're going to get an upright, enlarged virtual object. Pretty cool. All right. So the other type of mirror is a convex mirror. And these, or diverging mirror, as it's also known, you're going to use the same rules that you just learned before. But now what's going to happen is that image is actually going to be formed a little bit differently, and it's not going to be as complex as it was with the concave mirror. Okay, so let's go ahead and do it. So with a diverging mirror, you're going to draw a P ray straight across, just like you did before. P ray straight across, and it's going to actually bounce off, and it's actually going to bounce off, and this ray is, if you could continue on the this imaginary line or this virtual line down through the focal point on the other side of the mirror, because this is the center of curvature, right? This is the curvature, so the radius has got to be over on this side, and the focal point is at 1/2 that radius. So that means this line is actually going to have a virtual line drawn down through the focal point, and that's the parallax ray. You're going to then draw another ray down through that focal point, and then it's going to continue on as a virtual line. Okay, so you can draw it down through that focal point, right? And when it hits the mirror, it's going to have a virtual line, and when it bounces off, the bounced off part is actually going to be crossing that parallax ray. You could then draw another ray, and they've drawn this where it just goes straight down through the radius, the curvature radius. And if it hits there, it's going to bounce off and come back out in the same direction that it went in. And it would be going down through that curvature ray. So this is a little bit different, okay? So you have to do this center of curvature ray just like you did before, okay? Actually, hold on a second. Let me just check something. This is a little bit different. They're saying this. They want you to draw a center of curvature ray, just like we did here. Oh, look at that. And then it comes up right through there. So pretty cool. So not only, there's actually a fourth ray that you could draw, a center of curvature ray that will actually bounce off that in the same way that it came in. But the center of the mirror ray is coming in, and it's forming a virtual image on the other side. This type of image is going to be upright, it's going to be reduced in size, and since it's on the other side of the mirror, it's going to be called virtual. So here we go. So this kind of brings us to these practical problems. Where, have you ever looked at yourself in an ornament, a shiny ornament on a Christmas tree, or something shiny that's rounded like a shiny a sphere that's shiny, and you look at yourself and you kind of look, well, kind of morphed a little bit, kind of like cute puppy nose videos where the camera lens gets too close to the puppy and their head is enlarged and the body is small. Well, that's kind of what's happening here. This is a diverging, it's actually a diverging mirror or a convex mirror problem, just like we did here. Okay, just like we did here. And so what's happening is your image is actually being formed on the other side, right over here, and you're seeing a very kind of distorted image of yourself, right? So you're seeing, this is where you are, you're seeing a distorted image of yourself. So this image on this last problem that we did would look distorted, kind of like that. Distorted and very small, smaller than you, right? If you're 6 feet tall, this image is not going to be 6 feet tall. It'll be very small. And it'll be kind of distorted looking, right? And so this is the ray problem of a convex mirror or a diverging mirror. Practical applications that we have is the Hubble telescope. We used a curved mirror to actually, when we first sent up the Hubble telescope and we turned it on, the images coming off were distorted, right? And what they had found out in this convex mirror, actually it was a concave mirror, it was too shallow by 1/50th of a human hair. So that focal point where all the lines were to focus weren't focusing at the proper place. So it was off by 1/50th of a human hair. And so what they had to do is they had to actually send up another lens, and give it almost kind of like give the Hubble telescope its own little glasses, right? Its own little glasses. And when they corrected for that 1/50th of a human hair, the images came out perfectly and very sharp. So it's pretty cool. And you could use you could use lenses to focus light at you could use mirrors to focus light at a point, and you could then analyze that and see stars from across the galaxy. Really neat. Anyways, I hope you enjoyed this about spherical mirrors. Okay, I will see you when we talk about lenses next.